There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, with oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the signs, sodium for salty times, magnesium, aluminium, silicon.
A solid is characterized by particles arranged such that their shape and volume are relatively stable. The constituents of a solid tend to be packed together much closer than the particles in a gas or liquid.
Because solids are so tightly packed, the atoms vibrate together in place.
The molecules in a crystalline solid have a uniform structure and shape. There are 4 types: metallic, ionic, covalent, and molecular.
Metallic crystalline solids are solids that are held together non-directionally in a sea of delocalized electrons.
Alkali metals and alkaline earth metals are examples of these metallic crystalline solids. Because of how the electrons are structured in relation to each other within the crystalline solid, the metallic solids conduct heat and electricity, but because the molecules are close together and the solid is still malleable and ductile. They also have strong bonds and strong intermolecular forces. Metallic crystalline solids also form alloys. Brass is a substitutional alloy, meaning some metal atoms replace other atoms of the same size. Steel is a
interstitial
alloy, meaning smaller atoms fill the holes the larger lattice atoms form. This picture depicts crystalline solids in a structured symmetrical formation. The right picture shows an amorphic solid, which is shown later in the presentation.
Ionic crystalline solids are a lattice structure of alternating positive and negative atoms with strong polarized bonds holding the ions together. Therefore, they are non-conductive unless melted. Strong ionic bonds and intermolecular forces and high boiling point. For example, salts.
Covalent network solids have electrons that are shared equally between atoms of similar electronegativity, so the bonds are very strong. These solids have high boiling points and they are non-conductive. For example, carbon in the form of diamonds, silicon dioxide, silicate, and glass.
Molecular crystalline solids are arranged in a regular lattice structure of molecules. These have weak dispersion forces, so they have low boiling points. Ice is an example of a molecular crystalline solid.
Amorphous solids have no order or structure between molecules. In this picture, you can see the difference between structured crystalline solids and the disorder of amorphous solids. Wax, glass, plastic, and styrofoam are examples of amorphous solids.
A liquid is one of the states of matter. The particles in a liquid are free to flow, so while a liquid has a definite volume, it does not have a definite shape. This is an example of how liquids move and interact.
Properties of liquids are viscosity, surface tension, and capillary action. Viscosity is shown with honey, which has long chains of molecules that are held together with hydrogen bonds, making them very sticky. It is also shown with fats and oils, which are nonpolar carbon chains with strong dispersion forces. Surface tension is when liquid resists increasing surface area. Cohesion is water being more attracted to other water molecules than anything else, creating surface tension. Molecules are stabilized by being attracted to other water molecules, so the outer water molecules are less stable and being pulled into the liquid, forming a higher surface tension. Capillary action is when a tube is placed in water and the molecules of water are more attracted to the glass or other substance of that tube than to other water molecules, so the water will climb up the tube and above the water line. Mercury is an exception to this rule, and the liquid mercury will go below the liquid line in the tube because the mercury molecules are more attracted to each other than to the glass or plastic. Examples of viscous liquids are honey and fats or oils.
The heating curve of a substance shows phase changes from a solid to a liquid to a gas. As you go up the heating curve, it's endothermic. As you go down the heating curve, it's exothermic. This heating curve is an example of one from water. As you can see, where it's 0 degrees Celsius, there's a plateau. This is the melting and freezing point. This is where the liquid, in this case water, changes from ice back to liquid water. The second plateau at 100 degrees Celsius is the boiling and condensing point, where the water goes from liquid to steam. In these plateaus, there isn't a change in kinetic energy, but there is a change in potential energy. The three slopes of solid, liquid, and gas have a change in kinetic energy, therefore there's a change in temperature.
This is the heating curve that you just saw on the graph in real life. A solid liquid ice turning into steam. The melting point of a substance is the energy needed to melt 1 mole of the solid at 1 atm, or 1 atmosphere. The freezing point always equals the melting point. Melting point is an endothermic reaction, but it is exothermic when it is the freezing point. Water melts at 6 kilojoules per mole. Vaporization point is the energy needed to vaporize 1 mole of a liquid at 1 atmosphere. Water vaporizes at 2,260 joules per gram. Boiling point always reflects the strength of intermolecular forces within the substance. If something has strong intermolecular forces, the boiling point of that substance is always high. The higher altitude something is at, or the lower pressure, the lower the boiling point. Temperature and pressure are always directly related. Normal boiling point is at 1 atmosphere, or sea level. Superheating can also increase or decrease the boiling point, making it easier to boil a substance. Melting point is the temperature at which a solid and liquid have equal vapor pressure. Normal melting point, the melting point is at 1 atmosphere or sea level. Supercooling can also decrease the melting point, making it easier to melt something. The main differences between a solid and a liquid is a solid has a stronger connection between molecules. The particles are more condensely packed and vibrate together. They're not able to move freely. Molecules within liquids are able to move more freely against each other, making the substance in a liquid state not have a definite shape, though it does have a definite volume. The viscosity of a liquid and how the particles move together is determined by the intermolecular forces between the molecules within whatever substance the liquid is.
Thanks for watching our presentation!